Dear friends, let us continue with our discussion of the basics of vectors. In the last lecture, we have seen how we can combine vectors, say vector A and vector B, addition of vectors. We have seen vector addition is commutative and also associative. We have learned how to express a vector in terms of ijk vectors, ijk unit vectors. Ijk vectors are unit vectors along the three directions, x-axis, y-axis and z-axis, the positive direction of x, y, z-axis in a right-handed coordinate system. These ijk vectors are unit vectors, means their magnitude is unity and they have no dimensions or units. These unit vectors can be moved over to any point in space, or they are not fixed vectors. They can be moved over. The direction remains the same, their magnitude remains the same. There are fixed vectors, they cannot be moved. For example, if you have a vector like say a1 xyz I plus a2 xyz j plus a3 xyz k. This is a vector that depends on the position variable. At different points in space, this vector is different. Such vectors are position dependent. They cannot be moved over. They are defined at a point. You cannot add a vector A with a vector B defined at a different point. If vector B has components, say b1 xyz, b2 xyz, you can add only for a combination of xyz, which is the same in both these cases. That is, we cannot add vectors which are defined at different points. They have to be added at the same point, defined at the same point. Now let us see vector multiplication. We have already seen how vectors are multiplied with scalars. That is, for defining the position vector r, we have written it like this: xi plus yj plus zk, where ijk are the unit vectors and xyz are the coordinates of the point whose position vector is r. X, y, z are scalars having the dimensions of length x, y, z. Therefore, we have already multiplied this unit vector with a scalar, this unit vector with another scalar, and the third unit vector with yet another scalar. That is, scalar addition we have already seen. When we multiply a vector with a scalar, for example, a vector A multiplied with a scalar C, if the scalar has no dimensions or units, then this vector simply gets multiplied and its magnitude changes to c times the magnitude. The magnitude of this vector is c times the magnitude of the vector. Magnitude is c times the magnitude of the vector. If c is minus 1, the vector becomes c. If c is minus 1 without any units, then CA will be equal to minus A. This is a vector having the same magnitude but oppositely directed. If this is a vector, if you multiply it with minus 1, we get the vector oppositely directed having the same magnitude. If you multiply vector with a scalar c, if c has dimensions or units, then the resulting vector is a different vector of a different nature. For example, velocity of a particle is a vector quantity. Suppose you multiply this velocity with a scalar m, mass of the object moving with velocity v, mv is known as momentum of the particle. That also is a vector, but of a different nature, because the dimensions of the quantity p is different from the dimensions of v, because we are multiplying v with a quantity, a scalar quantity having dimensions and units. The scalar multiplication, what we have already seen is the unit vectors, they can be moved over from one point to another without any change. Whereas for any case, vector addition can be performed if we have to look at the situation, whether it is conformable for addition or not. Now let us come to vector multiplication. Vector multiplied with a vector. There are two kinds of multiplications for vectors with vectors. One is the scalar multiplication, scalar product. Another name is dot product. And the second case is the vector product. Cross product. First we will see scalar product, vector multiplication. With vectors. One, scalar product. Second, vector product. Today we will see scalar product, how scalar products are found. If you have a vector, say A, and another vector B, and if they make an angle theta between them, there is an angle theta between these two vectors A and B. A and this is B. This angle is theta. Of course, this angle is not taken, this angle is not theta. The smaller angle between two vectors, you can consider two angles. One is this, the other is this. The smaller angle is the angle between the two vectors. Then the dot product A dot B is defined as AB cos theta. This product is a scalar. That is why it is called scalar product. The resulting quantity being scalar. A dot B, it is written like this, A dot B. A dot B is A B's cos theta. The magnitude of the first vector, with the product of the magnitude of the two vectors times the cosine of the angle between the two. It can be looked upon as, if A and B are vectors, then A, B. You take the projection of vector B on A. This is A, B cos theta. Projection, if this is theta, the projection of B on in the direction of A is B cos theta. That multiplied with A, the magnitude of A B cos theta. This is A dot B. You can also consider another projection. Instead of taking this projection, if you take a projection the other way, then what we get is B times A cos theta. Both are, this is B dot A. B dot A is equal to BA cos theta and A dot B is AB cos theta. That means both simple multiplication of A multiplied by B, AB and BA are equal. Therefore, B dot A is equal to B dot A is equal to A dot B. Scalar product is commutative. It is not depending on the order of multiplication. The product is A dot B is equal to B dot A. Now let us consider a vector expressed in terms of two vectors expressed in terms of the ijk unit vectors. Also, let us first see what about the dot product of the unit vectors among themselves. I dot I. What is I dot I? Between two vectors I and I, defined by I vectors, what is the angle? Angle is 0. From our definition, I dot I is equal to 1 multiplied by 1 multiplied by cos of the angle. Angle is 0. Cos 0 is 1. Therefore, I dot I is 1. What about J dot J? J dot J is also equal to 1. K dot K. In a similar way, we can find that the ijk vector, from among the ijk vectors, I dot I is equal to 1, J dot J is equal to 1, K dot K 1. Now what about I dot J? I dot J. Again, applying the same rule, 1 cosine of the angle between the two. The angle between I and J is 90 degrees. Therefore, cos of 90 is 0. Similarly, I dot J is equal to J dot I. Both are 0. I dot J is equal to J dot I is equal to 0. Also, J dot K is also 1 multiplied by 1 cosine of the angle between the two unit vectors J and K. That is also 90 degrees. Cos 90 is 0. That is, we can find that I dot J is equal to 0. J dot K is equal to 0. K dot I is equal to 0. Also the reverse order also 0. Thus we find that with the help of these properties we have listed for the unit vectors, we will be able to find the dot product of two vectors expressed in terms of the ijk unit vectors. AB, the vector, A is equal to, say, AX I plus AYJ plus AZK. And B, vector B is equal to BX I plus BYJ plus BZ K. Now let us find A dot B. A dot B is equal to, first take the first term of vector A and multiply, take the dot product with every other terms of B. Ax, Bx, Ax, Bx, I dot I, Ax, By plus Ax, By, I dot J plus Ax, Bz, I dot K plus, what about I dot I, that is 1? What about I dot J, that is equal to 0? I dot K, K dot I and I dot K are equal. I dot K is equal to, K dot I is equal to 0. Therefore, only the first term survives. In a similar way, with the multiplication with the second term for the second vector, the one term that survives is B, Ay, By, J dot J. Every other product will be vanishing. The last term, for the last term will be with this thing, Az, Bz into K dot K. Thus we can write Ax, Bx plus Ay, By plus Az, Bz. So the dot product of these two vectors is Ax, Bx plus Ay, By plus Az, Bz. What about the angle between the two vectors A and B? How can we find that? Vector A is given by Axi plus Ayj plus Azk, and B is given by Bxi plus Byj plus Bzk. The two vectors are written in terms of their components Ax, Ay, Az, Bx, By, Bz. Now A dot B, let the angle between the two vectors be theta. A dot B is equal to magnitude of vector A multiplied by magnitude of vector B. This is A dot B. Magnitude of vector B times cosine of the angle theta. What about modulus of A? That is equal to square root of Ax square plus Ay square plus Az square. What about this? That is again square root of Bx square plus By square plus Bz square to cos theta. But we have already taken, with the help of the components, A dot B is evaluated, and that we found as equal to Ax Bx plus Ay By plus Az Bz. That is, A dot B can be defined in terms of its the magnitudes and the angle between them, like this, and in terms of taking the dot product of the components with each other, we can find it to be Ax Bx plus Ay By plus Az Bz. Therefore, these two are equal. Therefore, cos theta is equal to Ax Bx plus Ay By plus Az Bz square root of ax square plus ay square plus az square multiplied by bx square plus by square plus bz square. Thus we can find the angle between two vectors defined, each of them defined through the ijk vectors and the projections on the xyz axis or the components along the xyz axis. We can find the angle between the two vectors like this. We will see one application of this method to find the angle between two vectors. This is the x-axis, this is y. I have chosen a cube. This side, this corner, this edge forms the x-axis, this forms the y-axis. You turn a screw in such a way that it goes from x to y, then the screw will, right-handed screw will advance in one direction, that is into the plane, into this direction, that is chosen as the z-axis. Now, unit vector I is parallel to this x-axis and y-axis unit vector j and z-axis unit vector k. So we can write down the position vector of this point with the help of unit vectors. Say unit, let the side be of unit length, therefore let the side of this cube be of unit length for the sake of simplicity. Then the position vector here is given by, say, r is equal to r1 is equal to x I multiplied by 1 unit x plus j. What about the corner here, the position vector of that corner? Because we have to define it in terms of y and z axis. R2 is equal to j plus k, because we have chosen a cube of side unity. What about this angle between these two vectors? This is one vector, this is the other vector. What is the angle between these two vectors? Suppose you measure this angle, that is 45 degree, this is 45. But the plane containing these two corners, these two lines make an angle with each other. That angle, let that angle be equal to theta. Let us find what that angle is, theta, for which we can take what about the magnitude of R1? Magnitude of R1 is equal to, say, square root of 2. What about the magnitude of R2? Is square root of 2, because it is coefficient squares, 1 square plus 1 square, square root. That is the magnitude of vector R1. For vector R2, it is again root 2. Now from our definition of R1 dot R1 is equal to magnitude of R1 times magnitude of R2 times cos theta. In terms of these ijk vectors, we can easily find R1 dot R2 is equal to I dot j 0 plus I dot k 0. What about j? J dot k, j dot j 1, j dot k 0. Therefore, R1 dot R2 is 1. That is the result is 1. Then substituting for R1 and R2, the modulus of R1 and R2, we get root 2 cos theta is equal to 1 or cos theta is equal to 1 by 2. Theta is equal to cos inverse 1 by 2. What is that? That is 60 degrees. Thus we have seen that the angle between the two vectors, these two vectors, the right-handed coordinate system defined with the help of, this is x, y and z. X to y, you turn, the screw will advance. This is z axis. You have two vectors, position vectors of these 2 points, neighboring sides. The diagonals of the neighboring sides make an angle with each other. Theta is given by 60. This can be easily found with the help of this dot product operation. Now let us go to the vector product or the cross product. If there are two vectors A and B, then the cross product is defined as a vector whose magnitude is given by A cross B. Its magnitude is given by A, B sine theta, where theta is the angle between the two vectors. AB sine theta, this is the magnitude of the vector. The product, vector product, say A cross B. What about its direction? Suppose you turn this A to B, if you turn, in what direction the screw advances? If you turn it like this, from A to B through the smaller angle, this way, then the screw will advance away from the board. That direction is chosen as the direction of the A cross B vector. Depending on, it can be found with the help of the right-hand rule. If you turn it in what direction, the right-handed screw will advance, will govern the direction of the vector. Now with the help of the ijk vectors, this can be taken care of and the vector product can be easily defined. Suppose A vector is given by, suppose you consider the I vector and take the cross product with the J. What about the angle between the two vectors I and J? I and J are perpendicular to each other. Therefore, the magnitude of I cross J is equal to, because magnitude of 1 sine 90 is 1. Therefore, the magnitude is given by I cross J, the magnitude is unity. What about this direction? Ijk vectors, if you take the right-handed coordinate system, x, y, z axis is taken like this. This is I vector, this is J vector, this is K vector. I cross J will be a vector which is away from the board, that is along the K direction. Therefore, I cross J can be written both in magnitude and direction like this, K. It gives both the magnitude and direction of the vector. What about J cross I? J cross I will be having J cross I. J cross I will be minus K. In a similar way, we can define cross product for other unit vectors. Say J cross K is equal to I. I cross J is defined K. I cross J, J cross K, K cross I is equal to j. If you take, the order is changed, the right hand side there appears a minus sign. That is A cross B. Generally A cross B is equal to minus B cross A. A cross B is equal to minus B cross A. These products are I cross J, K, J cross K cross I. If you take J cross I, that is equal to minus K. Similarly, if the order is changed, it becomes negative. With the help of this definition, the basic cross product operations for the ijk vectors, we will be able to write down the cross product of two vectors expressed in terms of their components and the orthogonal triad of unit vectors ijk. How that is done, we will see. Vector A cross B, we have to write this as Ax I plus Ayj plus Azk cross multiplied, cross operation Bxi plus Byj plus Bzk. What about I dot I? I cross I. I cross I, J cross J, K cross K. What about them? Their magnitudes. I cross I. If you find the magnitude, you find 1 multiplied by 1 multiplied by sine of the angle between the two. Between I and I, the angle is 0. Sine 0 is 0. So, this cross product vanishes. I cross J is K. J cross J plus Ax Bz. I cross K. What about I cross K? Is minus J plus Ayj, Ay Bx, J cross I. What about J cross I? J cross I. I cross J is known. This is minus K. The second case is Ay By J cross J, that vanishes. The third is Ay Bz, J cross K, J cross K, minus I. Then third term plus Az Bx, K cross I, K cross I is minus J plus Az By, K cross J, K cross J, K cross J minus I. Let us examine that we have made a mistake. Ax times Ax, this vanishes. I cross j is k. Next is Ax bz. I cross k. I cross k is minus j. Now ay bx, j cross I minus k. Ay bz, j cross k. J cross k is I, not minus I, it is I. Then last one, Az times bx, Az bx, k cross I is j plus j. This last one, k cross I. The last, Az by, k cross j is minus I. We have two terms with minus sign, three terms with minus sign, and three terms with plus sign. Now we can group them together and express them in terms of ijk. That is, A cross B is equal to, let us write down the items, Ay bz minus Az by times unit vector I plus j terms. Az bx minus Ax bz j k terms. Ax by minus Ax bx, sorry, Ay bx k. Therefore, A cross B will be Ay bz minus Az by times unit vector I. Az bx minus Ax bz times j vector plus Ax by minus Ay bx times k vector. The cross product of two vectors, we see they are non-commutative. A cross operation is non-commutative. A cross B is not equal to B cross A, but it is minus B cross A. This is how it is found. And not a simpler way to remember these things. In terms of ijk, we can write the cross product as A cross B is Ax, Ay, Az, Bx, By, Bz, determinant. If you evaluate this determinant, then you can find that to turn out to be this formula. So this is an easier way to find the cross product of two vectors A and B. And there are several physical situations where we have to find the cross product of two vectors. For example, torque vector is equal to R cross P is torque. R cross P is torque. Sorry, R cross F. So torque is R cross F. Torque. You can define an area as a vector because in several situations we need to take the projection of a vector perpendicular to a surface. For that purpose, it is convenient to treat area as a vector. For area vectors are defined as two vectors in that plane whose cross product will be giving A cross B will be giving its magnitude of that vector will be the area, and the direction will be can be chosen appropriately depending on how you choose the the vectors lying on that surface. With that, let me stop here. Thank you.